Hello, everyone, and welcome back to Indian Genes. We have an absolute special episode for you today. It's exclusive coming to you from Indian Genes. Our guest today, I would like to say, is a friend of this show, has been here before, has spoken to us, and was one of the people that spoke to us, in fact, very early in the show when very few people were listening to us. I'm really happy to give him some information about what we're doing now, which is heard in over 65 countries. We've cost about 200,000 views, but it's about him right now. And I'm not really going to spend too much of time on his introduction because I think you all already know him, and I'm going to try something different, a small introduction, and let's see whether he accepts that. So, everyone, our guest today is a curious farm boy, Avi Loeb. Welcome, Avi. And I didn't, my thought was if I took time to introduce you, I would be spending 15 minutes. I'd rather talk to you and let people listen to you. I hope that was fine.
Yeah, we live for a short time. Let's make the best out of it.
Perfect. So, welcome back, Professor. And there's so much that's happened since we last spoke, but I'm going to let you take on this from here. Initially, if you want to give us a little brief introduction, maybe people are just tuning in, and what exactly you are doing, and what is the latest exciting news from, especially Project Galileo.
Yeah, so I'm a theoretical astrophysicist, and I had many leadership positions, founding director of the Black Hole Initiative, the chair of the astronomy department at Harvard, and currently the director of the Institute for Theory and Computation. But what gives me the greatest pleasure is to discover something new about the universe. And I just recently, I write an essay every day or so, and I recently reasoned that being a scientist is a great privilege because you don't need to aspire to get recognition from journalists, from influencers, from prize committees. The biggest award, the biggest prize in pursuing science is understanding something fundamental about our cosmic neighborhood. And the most fundamental question is, are we alone? I would give all the money in the world, all the prestige in the world, just for knowing whether we have a partner in our cosmic neighborhood. That would be enough for me, just knowing that. I don't need anything else. And because it will change the future of humanity if we find out that we are not the smartest kid on the block, if we can learn from someone that developed technologies and science well beyond what we currently possess. And so I'm leading the Galileo project at Harvard University, and we have several avenues of research. In the past 70 years, people searched for radio signals, but it's just like waiting for a phone call. Nobody may call you when you're waiting. A different approach is to search for packages in your backyard. Maybe someone sent them, and even if the sender is dead, you could still find them. And so we are looking for objects near Earth that may have been manufactured by an advanced technological civilization. You can think of it as space trash. And the way I think of it is that their trash is our treasure. I mean, we send to space probes that will not be functional in hundreds of years from now, and they would constitute space trash. And we also, I mean, Elon Musk launched the car, the Tesla Roadster car, into an orbit around the sun. And, you know, in 20 million years, it might collide with Earth. And all I'm saying is we should be open-minded. We shouldn't argue that anything in the sky is a rock, including things that do not look like rocks that we are familiar with, because there might be technological gadgets. And so we built an observatory at Harvard that is monitoring the sky 24/7, because the US government reported about objects they cannot understand, the director of national intelligence. And in fact, there might be a hearing within a month in Congress, the US Congress, discussing these objects. Now, it's possible the US government simply cannot figure out what these objects are because they are not a scientific organization. So we don't rely on them. We are looking at the sky. The sky is not classified. And we built a new observatory that uses new instruments in the infrared, optical, radio, and audio. And we analyze the data with machine learning, artificial intelligence software to figure out if everything we see is familiar. Is everything clouds, birds, airplanes, drones, balloons, or is there something that is not familiar? And we have a new paper that is about to be finished by the end of this month. We will post it publicly, where we analyzed nearly 1 million objects on the sky over the past few months, and we give the results. Separate from that, I mean, we are building 2 additional observatories that in different locations that will give us additional data. So hopefully within a year, we'll have 3 operating observatories with millions of objects that we monitor. And then in addition, we are also studying objects that collide with Earth. These are meteors. And there was one meteor from a decade ago, 2014, that US government satellites spotted, and it was moving faster than the escape speed from the solar system. So it came from interstellar space. And in fact, even outside the solar system, it was moving faster than 95% of the stars in the vicinity of the sun. And it exploded in the lower atmosphere, where the density of air is quite high. And so from that, we inferred that its material strength was tougher than even iron meteorites. So it was a very unusual object, and I was wondering, could it be technological in origin? So I led an expedition to the Pacific Ocean of the Galileo project. We recovered materials, and we found about 10% of the molten droplets, meteoritic material that we recovered, has a composition that is different from solar system materials. But we still do not know the nature of this object, so we hope to go again in summer 2025, and this time use a robot with a video feed to pick up bigger pieces of the objects in the wreckage that was left from that meteor. And finally, I should say that we will be looking in 2025 for more objects that might be interstellar that are passing near Earth. The first one discovered was Oumuamua by a telescope in Hawaii. It looked very weird, most likely flat, and was pushed by some mysterious force away from the sun, acting on it in addition to the force of gravity. And so it remains mysterious, and we want to get more data on future objects like it. And there will be a new observatory called the Rubin Observatory in Chile that will use a 3.2 gigapixel camera, 1,000 times more pixels than in your cell phone camera, and will monitor the southern sky every 4 days. And there is a good chance that every few months it will discover additional objects like Oumuamua. And hopefully we now can look at them with the Webb telescope and learn much more. So my general approach is that the more data we have, the better, because if the data is limited, many of my colleagues argue, well, it's a rock of a type that we've never seen before. And they dismiss and ridicule any discussion on something that is not natural. But if we have a lot of data, they will have no way to escape a conclusion that it does look as an artificial object if it is. If it's not, then that's fine. We learn something new about rocks. So no matter what, it's good to have as much data as possible. And in the first detections of interstellar objects, people just assumed that it must be rocks. Now we know that some of them look really weird, and we should therefore collect as much data as possible to figure out their nature.
That's amazing. I just wanted to get back to the latest paper, and you've just spoken about the Galileo project, where I think you and your team had mentioned that 78% of, I think it's called the IM1 spirals, if I'm not mistaken, or the
Right.
chemical classification, when that was done. Now, I did go through that, and when you say 78% of it was from originally ancient parts of the universe, or that material was from there, I was trying to figure out, and maybe you could simplify it for us. What is the other 22%? And
Yeah.
where do you see
So
an anomaly?
So we recovered about 850 molten droplets that look like they were exposed to very high temperatures. And we found 78% to be of solar system origin. These are what we call cosmic spherules that resemble things that were found in the past in many other locations and can be explained as residue from material from the solar system. However, 22% of these 850 spherules, which by the way are less than a millimeter in size, they are smaller than the size of a grain of sand. 22% of them looked different in terms of the composition. We call them differentiated spherules. And by differentiated, what we mean is that there are some elements that have a much higher abundance than solar system materials from the material that made all the objects in the solar system. And one way to differentiate some elements and make them more enhanced, it could happen, for example, on a planet that is molten, like the Earth was early on. What happens then is that some elements have affinity to iron, and the core of the Earth was made of iron. So those elements with chemical affinity to iron, they sink to the center, and they leave behind some elements that are overabundant. So we found that 22% do show a pattern of abundances that resemble a situation where you differentiate some elements relative to others. But out of those, about half, so that is 10% roughly, or 11% of the total population, have differentiation that is not similar to any of the objects in the solar system. It doesn't look like the crust of the Earth, doesn't look like the moon or Mars or asteroids. And we say that the origin is unknown. It's potentially not from the solar system. But to find out specifically what the object was, we really need bigger pieces, because some of the elements were volatile and they evaporated during the explosion of this meteor. And if we find bigger pieces, we can trace them, because they can evaporate only from tiny droplets, but not from bigger pieces of the object. You can think of the analogy with a computer, that a laptop that you throw into the fireplace. If it gets melted, you will get tiny droplets out of it. You can infer an unusual chemical composition of those droplets, but you won't be able to figure out that the original object was a laptop necessarily. However, if you find some pieces of the screen, that will give you much better clues. Or if we find, the core of a Tesla Roadster car at the wreckage, that obviously tells you that it was technological. So we aim to find bigger pieces, bigger than a millimeter, hopefully centimeter or bigger. And the other advantage is that once you find those bigger pieces, we will be able to do isotope dating analysis, meaning we can infer the age of the material and demonstrate from how far it came, and that it's different from the age of the solar system. All the materials in the solar system have the same isotopic age, because they came from the same cloud of gas. But if something came from far away, it will definitely have a different age, and we can tell how old it is. Of course, the biggest challenge would be if I find a gadget at the bottom of the Pacific Ocean and it has buttons on it, should we press a button?
And as you mentioned, interestingly, because when we read about it in scientific journals, or you're reading as a common man, and we are not really experts at this, what I found interesting in that article also was where you had mentioned, or your team had mentioned, that this particular spirals could be in some form we holding meteors in our hands. And I think the term there that was used was tidal wave disruptions that could have happened through space. Now that was something very different, because when we talk about tidal disruptions, it's you got to try to picture what you're saying here, right? Because you always use the word tidal waves with water and you're used to it locally. But when you're talking about a tidal disruption in space, that disrupts everything around it as well. And is that what y'all were trying to say when you mentioned about it?
So let me explain. So in fact, there are two possible origins for that object. Either it's natural or artificial. If it's natural, the question is what produces this unusual abundances of elements? And together with my postdoc, Morgan McLeod, I came up with an idea that you can, in principle, produce this abundance of elements by taking a planet like the Earth and bringing it very close to the most common type of star, a dwarf star. So most of the stars are 10% of the mass of the sun. And they have roughly a size that it is 10 times smaller than the sun. So altogether, they are 100 times denser than the sun. And that means that, if you bring the Earth close to the sun, it will not tidally disrupt it. It will not destroy it by the force of gravity. However, if you bring the Earth close to the most common star, a dwarf star, it's so dense that it could, in principle, spaghettify the planet and make a stream of rocks out of it. And since those are the most common stars, perhaps such a process is quite prominent in creating interstellar rocks. And that's the suggestion that we laid out in this published paper after the analysis of the materials from the Pacific Ocean. And so the idea is that if you have rocky planets like the Earth near the most common stars, dwarf stars, they can be thrown or kicked into an orbit that comes very close to the star by either a very heavy planet like Jupiter in their vicinity that scatters them or creates an instability that kicks them in that direction, or a companion star. And if those circumstances are common, then very often you will get a rocky planet being spaghettified, basically destroyed. And in the process of that happening, the planet comes very close to the star and gets heated to temperatures of thousands of degrees, when at which the rock is melted. And as a result of that, you get the differentiation that I was talking about. So some elements will stay in the outer layer of the planet and others will sink to the iron core. And the outer layer of the planet gets ejected at the highest speed. And I calculated that speed, and it felt like a eureka moment, because the speed that I got from the tidal disruption of a planet like the Earth in the vicinity of a common star, like a dwarf star, like Proxima Centauri, the nearest star to the sun, the speed is 60 kilometers per second, exactly the speed that was derived for this interstellar meteor. So there is a way of making such an object naturally out of a planet like the Earth passing close to a star like Proxima Centauri. But we don't know that to be the case, because we found only molten droplets. So hopefully after the next expedition, we'll know for sure what the origin was.
I think, correct me if I'm wrong, the very interesting term that I think you coined was the Milky Media. When the Milky Way does intersect with the Andromeda galaxy, you did put it together and say it would be the Milky.
So that is a different work that I've done about forecasting the future. When we look, especially from some locations on Earth, when you look at the sky, you see the Andromeda galaxy approaching us, and it's moving at a speed of about 100 kilometers per second towards the Milky Way, and it's on a collision course. And within a few billion years from now, when the sun will still be around, the two galaxies will collide. And I wrote the first paper that calculates the outcome of this collision together with my postdoc, TJ Cox, and that was about 15 years ago. And in the paper, we referred to the merger product of the Milky Way and Andromeda, and I decided to coin a short, an abbreviation for that merger product, and I called it Milkomeda, a combination of the Milky Way and Andromeda. The one interesting thing is the sun may be kicked out of its current location, and in the process of doing so, we could see the Milky Way from a distance. We might even be captured by Andromeda before it comes back again and merges. And of course, the Milky Way will not appear anymore as a strip of stars on the sky, because that's the result of it being a disk-like. We are embedded in the disk. We see the disk as a strip of stars on the sky. That's why we call it the Milky Way. After the collision, the two galaxies will merge to make a football-shaped galaxy that is called an elliptical galaxy. So the stars in the sky will be scattered. There will not be a strip like the Milky Way is now. And interestingly, this will be, if the standard cosmological model is correct, it will be the only observable thing in the sky in the long term, because all other galaxies away from us are receding from us because of the cosmological expansion. But we currently know that the expansion accelerates. And that means that every distant galaxy moves away from us at a speed that keeps increasing with time. And eventually, all these distant galaxies will reach the speed of light and exceed it relative to us. So we won't be able to see them beyond a certain time in the future. And we will be left in the dark. The universe will become very lonely. The only things we would see in the sky are the stars of Milkomeda.
And when you say that they're going to be expanding at the speed of light, and so that means what I can assume is the Milky Way is going to be expanding at the same time the Andromeda galaxy is going to be expanding. But it's counterintuitive when you say if the whole universe is expanding, then why are these two coming together to collide? It's
Right. So what one needs to compare is the force of attraction between the two galaxies to the repulsive force associated with the mean density of the universe, which is actually right now dominated by the vacuum energy. It's called the dark energy or the cosmological constant. So that introduces this expansion, accelerated expansion. But if you have a system that is much more dense than the cosmic average, that system doesn't care about the cosmic expansion, because within the region of that system, there are much stronger forces at play. And so that is true, for example, for an atom or our body. Our body is not expanding with the rest of the universe. An atom is bound by the electric force. So it doesn't care about the cosmic expansion, because the electric force within the atom is many orders of magnitude larger than the gravitational acceleration associated with the cosmological constant. So it's completely negligible. That what happens on the large scales in the cosmos is irrelevant. And the reason it's relevant on large scales is because the electric force can be screened. You have positive and negative charges that cancel each other, but gravity cannot be screened. So on very large scales, gravity dominates the dynamics of the universe. And the question is, what's on very large scales, the scale of the horizon of the universe, what controls gravity? It turns out that right now, it's not matter, it's actually the vacuum that controls gravity. It's called the cosmological constant, or the dark energy. And that creates these accelerated expansions, a sort of force of repulsive gravity, which is a result of Einstein's theory of general relativity, that when the vacuum dominates, it can produce gravitational repulsion that accelerates galaxies away from each other. But on very small scales, like the scale of the distance between Andromeda and the Milky Way, the density of matter is, thousands of times bigger than the mean average, the average cosmic density. And so as a result of that, we are attracted to the local group of galaxies. And so we end up in this dynamics of a merger between Andromeda and Milky Way. And that system will remain bound as a single galaxy, irrespective of what happens to the universe at large, simply because it has a much larger density. So the attractive gravity within this system overwhelms the repulsive force from the vacuum, which is much less dense.
Right. And when you were talking about the cosmological constant, is this also one of the reasons, or when Einstein did propose his theory, he was not really sure about it and wanted to put in a
Yeah.
different number and later on changed his mind?
So the story starts with Einstein thinking that a beginning in time is not very satisfactory, philosophically speaking, because then the question is what happened before that time and how did it, but so he thought the universe, any solution to his equations, he came up with the equations of general relativity. He published them in November 1915, and he wanted to derive a solution for the universe, assuming that the universe is uniform in density and isotropic, the same in all directions. And he wanted to find a solution that doesn't expand, because if the universe expands, it means that if you go back in time, there was a point in time when the density was infinite, and that's not good news, because his theory broke down, and then the question is what happened before that. So he wanted to find a static solution that is not expanding, and to balance the attractive gravitational force between matter particles, he introduced a cosmological constant, or the vacuum, that produces a repulsive force. And he thought maybe the two balance each other exactly, so that you get a steady situation where the universe is static. It's not expanding and not contracting. But later it became clear to him and many others that such a solution is not stable, because if you just introduce if you imagine a butterfly moving its wings, that introduces density inhomogeneities that will cause some regions to collapse or expand. You cannot maintain this stable disequilibrium by which gravity is balanced by the vacuum versus matter, because the matter either becomes denser in some regions as a result of fluctuations, or vice versa, and you end up with instability. So about a decade later, actually, it was clear from data that the universe is expanding, and then Einstein thought, well, it was a mistake on my behalf to imagine that there is this cosmological constant that he added to his equations, just as a way of balancing the attractive nature of gravity, but it can actually represent the vacuum. And then it turns out that indeed the universe is expanding, but there is some mass density or energy density to the vacuum. It's called the dark energy. It was discovered. The Nobel Prize was awarded for it. Actually, one of the young people who was involved in the discovery, Adam Rees, was a student at Harvard University when I arrived about 31 years ago. And I taught a class in cosmology. And he told me later that in my class, I talked about measuring cosmological parameters by measuring distances to light sources. And that gave him the incentive to, during his PhD, to use supernovae, exploding stars of a certain type 1A supernovae, to measure distances and infer cosmological parameters. And that won him the Nobel Prize. So he acknowledged that thanks to attending my class, he thought about this direction. So now we know that the universe does have a vacuum energy density, or a cosmological, something that looks like a cosmological constant. We don't know the nature of the dark energy. Einstein, in a way, by introducing it, was not wrong. It's just that the universe is expanding, but it has some energy density to the vacuum that is currently dominating. And the reason it's dominating in the last half of cosmic history is because early on it was negligible, because the universe was much denser. But as the universe expanded, eventually it got, the matter and the radiation got diluted enough for the vacuum to show up and dominate the mass budget. And so that's what happens right now. And that's why the dark energy, or the cosmological constant, is dominant, and it will become even more dominant in the future as matter gets diluted even more. Because the point about the vacuum energy density is that it doesn't change. Well, at least as far as we know, it stays constant as of now. And so as the universe expands, it's becoming more and more dominant, because everything else gets diluted.
Amazing. And the story that you just spoke about with the Nobel Peace Prize is truly amazing. And I wish all of us could have had a chance to attend your class. But for now, we'll have to make do with speaking to you online. I just want to get to UAPs. I think a lot of people want to hear your views on that. But just for one moment before I go there, I thought that you spoke about the cosmological constant. And based on that, when we reverse time, we came to the theory of the Big Bang. I want to connect it to what we were just speaking about Andromeda and the Milky Way. So, does this mean, if we apply the same logic, that the Milky Way itself, if you go back in time now, could be the combination of two other galaxies colliding, or was there
Yes.
not enough of time in the universe for
Oh
that?
no, that's exactly the way. So um, the way galaxies started is from very small building blocks, roughly 1 million times smaller in mass than the Milky Way, and those were the earliest galaxies to form. And in fact, my early work was about the nature and the characteristics of the first population of galaxies and stars. I have two textbooks on the first galaxies in the universe, and I was part of the committee, the advisory board that designed the Webb telescope, that with the idea that it could image the first galaxies. And we are getting there. In fact, the Webb telescope found galaxies from that were made in the first hundreds of millions of years after the Big Bang. And then it produced some surprises because some of those galaxies appear to be brighter than we expected. And that was actually my hope when I wrote my textbook about a decade ago. And I was asked about it. I said I would very much hope that when the Webb telescope gives us data, it would not necessarily agree with our expectations, because that would mean that we could learn something new. The beauty of doing science is that it's a learning experience. We should be humble because, nature is far more imaginative than we are. So it's always good to compare data to our expectations and learn something new from it. As we go back in time, the Milky Way did not exist. It was made of smaller building blocks, all the way back to maybe 100 million years after the Big Bang, when the very smallest building blocks were made, and they had 1 million times less mass than the Milky Way right now. And as we go back in time, of course, we get to a time when there were no objects whatsoever. It was just a soup of elementary particles and radiation. And that soup was hotter and hotter and denser as we go back closer to the beginning. The fundamental question is, what was there before the Big Bang? What created the Big Bang? The answer is we don't know. I was just asked in an email yesterday if there is any book that describes what happened before the first second. And of course, there are books talking about processes that could have taken before the first second after the Big Bang. But by no means we know what happened, because there are many possibilities, and we haven't yet observed that period of time in the first second. One thing we are missing is a theory that unifies quantum mechanics and gravity. These are the two pillars of modern physics. We don't have a predictive theory that unifies the two, and it's clear that we need it in order to go back to the Big Bang and before, because Einstein's theory breaks down when the density diverges, density of matter, and that's exactly what happens near the Big Bang. And so if we had a theory of quantum gravity, in principle, we could have gone back in time and figured out what were the conditions that led to our universe, what was there before the Big Bang. I can imagine that there might be another civilization that has a much more advanced science, because they came to exist around a star that formed maybe 1 billion years before the sun. Most of the stars formed billions of years before the sun. The sun is a late bloomer. So we are late to the party, and maybe another civilization figured out how to unify quantum mechanics and gravity. And what that means is, if you know how the universe started before the Big Bang, you have a recipe for creating a baby universe. And it's possible that a very advanced civilization can produce the conditions that led to the Big Bang in the laboratory. And that is very significant, because if you think about advertising the job of God, what would you put in the job advertisement? The one qualification is, if you want to apply for this job, you should be able to create a universe as God. And what I'm saying is that quantum gravity engineers could, in principle, apply for this job. And the question is, was our universe created in a laboratory by a scientist in a white lab coat?
Besides you putting out a job description for God and connecting it, I would connect it to what you said recently, where you mentioned that probably the least risk job was that of a scientist with all that is currently happening in the world around us, right?
Yeah, so I came to realize the benefits of being a scientist because I attended the Munich Security Conference in February 2024, and I noticed I spoke there, and I noticed that on the roof of the building there were snipers, and they were there to protect political dignitaries like Vice President Kamala Harris that attended the same event. And then just a few days ago, I was invited to an event in the Boston Museum of Science in the United States, um, and there I had a conversation with the crime author. I mean, she's a bestseller, Patricia Cornwell, and she came to the event with two bodyguards. And I noticed that nobody is guarding my body in both events, and that led me to reason that being a scientist is a much less risky occupation than being a high-level politician or a blockbuster crime author. Uh, and then also this week on Monday, just a few days ago, I had a podcast that became number one on Spotify. And on the same day, Kamala Harris had a podcast, the first podcast that she appeared in. And my podcast got more views than hers. And that was explained to me as the fact that science has a much more uplifting message to the public than political conflicts. So my conclusion from all of that is that being a scientist is a low risk, high reward occupation. And, it's amazing that I get paid for what I enjoy doing, that I would do any day, even without getting paid for.
You did mention low risk, and probably this is where I want to get straight away to the high risk that you are taking, not physically maybe, but in what you're proposing. With your paper recently published, you spoke about detection, characterization, and then identification of using a particular software to detect UAPs. Now, if we can, I want to just break this down into the same three parts and tackle this question. I'll start with first is the detection. So currently, what you are doing is exactly that. You're putting yourself out, you're going to places yourself, you are trying your best to detect. And a lot of people want to start the other way around, where they start identifying and characterizing. That can happen because if you don't have the proof for that, it's always good conversation, it's always fun. But let's first detect. And if you're open to detecting, because that's where the hard work is, that's where you have to put your money, then everything else becomes easier. So do you agree with that, that the harder work is actually going out there and trying to detect? Because we can all theorize, right? Even I can, without being a
Yeah,
scientist.
exactly. I mean, people often think that it's very important to have freedom of speech and everyone's saying whatever they think, and let Darwinian selection pick up the best ideas that will stick. But what they don't realize is ideas are really easy to come by. There are so many possibilities, and nature is just one of them. So if you are interested in the truth, in what describes the reality that we all share, then it requires hard work because you need to collect evidence and figure out, it's just like a detective story, figure out the one interpretation that is the most plausible based on all the data, all the evidence, and that's a lot of work. So most people prefer to have an opinion, and that is very legitimate in the context of politics. But my point is that science is better than politics. Why? Because there is an arbitrator, and that is nature. So you can have your opinions, but if you are sufficiently humble to allow the evidence guide you, then you might realize that you are not at the center of the universe, not physically and not intellectually. But if you insist that we are the smartest, and the fact that we might not be alone is an extraordinary claim that requires extraordinary evidence, then, and you are not seeking the evidence, you can remain ignorant for the rest of your life. Now, some people do prefer to maintain their ego and stay ignorant. That's not me. I mean, I would like to know the truth. And if we have neighbors, this will add the benefit of us being able to learn from them. Once we realize that we are not at the center of the universe, we could design a spacecraft that would reach Mars. If we thought that Mars orbits the Earth the way that most people thought more than 500 years ago, then we would never reach the destination, because we would shoot rockets that will go in the wrong direction. And therefore, I say that understanding reality has a benefit that you can adapt to it, even if it does not flatter your ego. And we, as humans, are always in pursuit of things that flatter our ego. We prefer to believe in wishful thinking. And that explains why a lot of people are attracted to put goggles on their head and live in the metaverse. You can live in the metaverse and have celebrities next to you, and you will feel very good about yourself. The only problem is it's not the reality that we all share. You can also get high on drugs. That's the attraction, that many people want to be high on drugs because it offers an escape from the frustrating reality that we all share. But a much better approach is to understand the reality and figure out ways of making it better and adapting to it and trying to improve it. And that is the path that I'm taking, and that's the path of science.
Right. And for people who are trying to get the hold around this last 3 years, who are not in the field, when you talk about UAPs, you have congressional hearings, there are people claiming that there was a report, there's a body. It's got a bit fuzzy. And I think you're the best person to give us some kind of, I'm asking you for a framework to actually
Right.
find out how to go about this. Who are we supposed to listen to?
Right.
I
So,
don't even
so
know
that,
which part of the journey we are on.
that's an excellent question. And what I often say is that nowadays we have large language models and artificial intelligence being trained on content produced by humans. And if you look at debates, what you find is that humans often get polarized. That's true in politics, where people prefer to belong to a tribe of like-minded people, and they keep hearing the same views and go to the extreme. And the same is true on the right or the left of the political landscape. And very few are in the middle trying to reason that both extremes make little sense and we should find a path in between. And if you wanted to train a machine learning software system on human-made content, you would be hard pressed to train it on content that represents what sounds like the most reasonable thing in the middle. On some items, it might agree with one side, on others with the other side, but there is not much content on that. Most people do not go in that middle path. And it's not only true in politics. What I'm saying is it's true, for example, in science. And the example that you brought up is the unidentified anomalous phenomena. So you have believers that would try to argue that we already have enough evidence and they are sure that we are being visited by technological equipment manufactured by other civilizations. And you have skeptics who say that everything in the sky is objects that we produced or rocks, natural objects. There is nothing else. And there are debunkers that basically try to kill any possible suspicion that there might be something anomalous. And I say that none of them, the believers or the skeptics, are doing the scientific work that we need to be done, and that is collecting evidence on objects in the sky. What can be simpler than that? Let's just put money into, we can get extraordinary evidence if we invest extraordinary funds in that search. We are searching for the nature of matter in the universe. Most of the matter is dark, it's invisible, we don't know what it is, we call it dark matter, and for 90 years we haven't found what the nature of dark matter is, and we invested billions of dollars in the search for dark matter. That sounds completely reasonable as part of the mainstream right now. Why wouldn't the search for technological objects near Earth be also part of the mainstream? After all, it will have a much larger impact on the future of society if we find evidence. So why don't we invest billions of dollars in telescopes and equipment and analysis of objects near Earth that could tell us whether all of them are rocks, or maybe among the rocks there are some extraterrestrial technological space trash? That sounds to me like the middle of the road that makes the most sense. But what I find is that common sense is not common. And, I hope that the situation will change. It's possible the US government has already some very interesting information, but they are classifying it and we don't know about it. If they do, I hope they will share it with scientists like myself, because my day job is to find out what lies outside the solar system. Their day job is national security.
Interestingly, you said common sense is not common, and I have thought about this, and my phrase would always be we are searching for, and the question is there intelligent life out there? I sometimes wonder whether we figured out whether there's intelligent life down here. And before,
Yeah, what I say, and I was actually on a panel led by Deepak Chopra just a few weeks ago, and one of the panelists, worked with Stephen Hawking, and Stephen Hawking argued that we should be really careful because there might be predators in space, that we should not reveal our existence. And I was asked about my opinion about that, and I said, well, if they are intelligent, they will avoid us, because there is a lot of room for improvement if you look at the geopolitics here on Earth, and we are not behaving very intelligently.
true. I just wanted to get to the next part of your paper after you spoke about detection and characterization. Would be next. Yes, this is probably midway once you do that. And over the last 3 years, I have detected a little bit of a change because people were always talking about intra terrestrial when you spoke about UAPs. And somehow I see a lot of talk now about intra-dimensional. I have seen this shift is becoming very obvious. And what is your thought on this? Are you open to when people talk about interdimensional as well?
Well, it's obviously possible. I mean, the reason they talk about it is because one of the attempts to unify quantum mechanics and gravity is done in the context of what is called string theory, that postulates that there are additional spatial dimensions, and all the particles we know about live in those dimensions as well. But somehow the extra dimensions are folded to tiny compact configurations, so we can't really see them. And so when believers in visitation by extraterrestrial objects talk about it, they borrow these terms of extra dimensions, and they say, well, maybe these are objects that are difficult for us to notice or are moving in unusual ways because they take advantage of extra dimensions. And those are people who are not practicing physics, so their idea about extra dimensions is not really constrained by all the experiments that we have in laboratories. If there are extra dimensions, they are really compact. It would not be possible to easily take advantage of them in navigating in the three dimensions that we know about, the three spatial dimensions. So, I would characterize these ideas as a complete speculation. Now, if we do have or see evidence for objects behaving in ways that cannot be explained otherwise, then obviously that's a possibility, but we are not there yet. we physicists work really hard to find new physics, and the Nobel Prize is awarded when tiny deviations from the standard model of physics are discovered. And there are very tight limits on the existence of extra dimensions or any way that they might manifest themselves in reality. So at the moment, I would just say that there is no basis for such claims.
A lot of us, we are worried because you said, as per the Fermi paradox, we are not as attractive on the dating scene. And so you think that they are probably more advanced, but it's just that there's too much of a distance to spend time on us.
Well, what Enrico Fermi did 70 years ago is ask the question, where is everybody? And that is a question that every lonely person asks. And what you tell those lonely people, you say, well, if you want to find a partner, uh, don't be presumptuous. Don't think that you are so attractive that they will come to you sitting at home. You need to leave your home and go to dating sites to find partners, or at the very least, open the windows and search for neighbors. And Enrico Fermi didn't do that. He was just having lunch at Los Alamos and asking, where is everybody? So I'm arguing that we keep thinking that we are at the center of the universe. And if anyone comes to visit us, is because they care about us. And my point is that we are completely insignificant. We became distinguishable from nature with our technologies only over the past 1 to 2 centuries. Uh, since the Industrial Revolution, the progression of modern science and technology. Before that, we were not that impressive. We just looked like other animals on Earth in the billions of years that the Earth existed. And so anyone arriving to our neighborhood with some means of propulsion must have taken a long time to get here, long before we existed. They don't have us in mind. We are not particularly impressive on if they arrive to our doorstep before we arrive to their doorstep. They don't really care about us, and what we should think about is benefiting from knowing about them rather than the other way around. And that's what people still are missing. And it's not, I think it's very presumptuous to imagine that we are alone, and the basic assumption should be that we are not, and let's just search for them.
So, to everybody listening, the last 2 or 3 minutes, unfortunately, was a little bit of a technical glitch, and we had to say goodbye to Avi Loeb due to a technical problem from my end. I would like to say that. But once again, I would like to thank him for the time that he spent with us. It was an amazing conversation. But rest assured, we will get Avi back on our podcast. And thank you once again for staying with us.